Welcome to this video. This video is going to be short. I'm going to discuss the data types of the telemetry packet. So all these data types that I have come up with are supposed to encapsulate all the four boards. So remember again, the CubeSat has EPS, OBC, ADCU, and the comms board, and the payload. That's around 5. Payload is like a sub system. So these data types are supposed to hold all of that data and to enable communication between different, let's say, subsystems, right, of the CubeSat. So what I'm gonna do here, I'm just gonna open the Zen mode so that it is more visible and more clear. Okay, so most of this data is not tested with the hardware, or rather these data types are not tested with the hardware. So it means that there are some types that I'll remove or add later when the hardware is ready. And all that depends on whether that data point is necessary and whether the packet that I am designing can be able to hold the size of all of this data. So what is my design approach? So my design approach in defining the data types, I've basically grouped the data types in terms of the boards themselves, right? So this will start at this point. The EPS, for example, EPS data is right here. So EPS data is the electrical power supply. Let me make this a little bit neater, a little bit like that, and then just like that. Okay, so looks better. Okay, so EPS basically has different components, right? And how I like to approach my designs is that if there is a component on the board, I treat it as an object. If it's a sensor, I treat it as an object, right? So I create a driver for it, an object for it, and then I call the low-level hardware functions to read that specific part, right? So for example, for instance, the BQ25703 is a back boost charge controller. You connect this with the solar and the battery and the VCs, or rather voltage, system voltage, and it's able to supply and prioritize those two, the input voltages and the battery voltages to supply the load. So basically, this is an IC that is connected through I2C to the MCU, right? So it has a lot of more data here. There's a lot of data that can be harvested from the BQ25703. But since this is, as I said, it's not hardware tested, I just have these two floats to test it. You can see I've written here to do, but this will come from the BQ25703 driver, right? So how do I encapsulate that data? How do I make it easier to use? I define a type, right? I define a type that is called the BQ2703 data T, right? So that type has two floats, right? The V system VBAT, and is a struct of floats, all right? And then EPS data now can use this type. It's a type by itself, right? So you realize that it's a nested struct. It's a nested struct. In addition to that struct, there are also other data types. There is the float, solar voltage, solar panel, solar voltage, current, power, etc. You can put this one in the struct, but you can only do too much abstraction. So I've just put them as part of the EPS data struct, and then defined that struct as an EPS data T. Then there's a regulator voltage. This is being measured by the current sensors. So you can measure the current sensor, current and voltage to 3V3 bus, 5 volts bus, and V6 bus. This is the voltage regulators data. Next is on board. These are miscellaneous operational data. So I have like a sense NTC on board. I have a set DS18, B20 on board also. It's an operational miscellaneous data. I can read it that way. When there is a function, there's a hardware function that allows me to detect whether that board, whether the EPS board is inserted on the CubeSat stack. So I can, these are binary, so it's a uint8 board detect can be a 0 or a 1. You can optimize here actually. You can optimize this one by saying use bit fields. You can use bit fields for that, but there's no problem. There's no reason to optimize it before we even test whether it works or not. But ideally, this a bit field would be very, very nice. Actually, because this is 1 bit, this is 1 bit, this is 1 bit, and this is 1 bit. These are 4 bits. You can fit all of that into a single uint8T. But this will also suffice. There's no problem with that. Memory for me is not a problem at this point, but I'll optimize that later. So this is the EPS data, right? That's the PCB for EPS will give me this type of data and more, right? Comms data, comms is basically transmission of telemetry from and to ground. So it receives command sequences, it transmits, it receives command sequences from the ground station, it transmits telemetry data to the ground station, right? But it has its own like operational data, like board temperature. For example, you want to know what's the temperature of the comms board. So there's a sensor that does that. There's a sensor on board that does that. Then it has things to do with, I'll define this later. It has things to do with, it has a memory, right? External flash memory. It has that, so you will find things like I'll need to know like uint16T, for example, what's the memory ID, right, or manufacturer ID. Let me just write here man ID like that. What's the manufacturer ID? What's things to do with uint16T memory? Because it's not very big, but it's memory size, things like that. So you realize that at one point I'll move this to, if they are for flash memory, and I've said that I like to design it around an object. I might say type def struct flash memory. Let's say comms flash, because there are flash memories on the OBC also. Flash mem. So I'll call this comms flash memory type T, right? Other data T. So I can take this and put it here, right? Put it right there, and then in the comms I can say now comms flash memory data T flash mem data, like that. So that just nests, rather makes the code neater, and you can like single out all the data you need for a flash memory, right? Flash memory, you can have things to do with 16, maybe 3 sectors, in 16T, maybe number of blocks for a memory, because I need all these data for like profiling the application, right? Yeah, so that's that, and then that is nested into the comms board data, that data T. So those are two boards, EPS board and comms subject to change, obviously, as I've been saying. The other board is the attitude determination and control board, this board right here. So that's that. So a DCS, attitude determination and control system, is basically used to read. The primary goal of this board is to read the inertial measurement data, right, or the movement and 3D position of the CubeSat. So it has components that read the inertial measurements, right? Like the ADXL 345 is a pure accelerometer, so it can give you acceleration on 3 axes, like plus other data, tilt, angle, etc. But for now, I've just written these three. Other data types are derived, like let's say you want to check the difference from, the tilt, for example, is derived from these three, but it's internal also. You can add it here, not tilt, right? Tilt. So of course this will come from the hardware driver I2C. You have the MPU 6050 data, which will give you, now the MPU 6050 is an IMU. It can give you angular velocity and acceleration on both, on all the 3 axes. So x, y, z accelerations, x, y, z angular velocities. Then you can derive the roll, pitch, and yaw from these data points. Yaw, you need to get the yaw, you need to have the magnetometer. So I have added the MLX 9033 magnetometer. This is its data struct. In terms of, it measures magnetism or magnetic strength on 3 axes, x, y, and z, depending on where you come from. So x, y is the flux, right? We have that data type. We have a GPS. GPS has a lot of data. I'm going to extract a lot of data from the GPS. So it means that, but the primary data, longitude, latitude, speed, and satellites, how many satellites are being used to resolve the position and the course. If this CubeSat is moving, ideally it's moving obviously in orbit, but you can get a lot of other data here. Azimuth angles, time, peaks, etc. That's it. That is its own data struct like that. Of course, they'll come from the driver as well. The other thing is sun sensors. We need to know the orientation of the CubeSat with reference to a given star. So I have six sun sensors and 2 analog to digital converters. So the sun sensors they produce analog signal, but the MCU is digital, so I need to convert. So I choose an external ADC. You can use the internal ADC, but I choose an external ADC simply because the external ADC will allow me to connect the ADC and the MCU using only 2 wires. That's I2C, right? SDA and SCL, right? If I had to use direct ADC on the MCU, I would use 4 pins for the first 4 solar panels, which is inefficient. So I have the ADS 1015 ADC. The first 4 solar, sun sensors are connected there. The last 2 are connected to the second ADC unit, right? All right. So finally, now we put all of these data points. We put now them as the ADCS data, right? So this is ADXL, MPU, magnetometer, GPS, and the ADC converters. We put them as now the nested structs to the ADCS data type T. Right, so we have 3 bolts are handled there. ADCS as altitude determination. We have comms, communication systems, DPS data, payload, right? So payload is payload is a camera. So this is a camera. So a camera is capturing frames of images, right? But those images will be stored on an SD card. Actually, they'll be compressed using Huffman compression, and then they will be stored. So this is the capture frames. There's another video that I'll make for designing and building the payload, and I'll go into more details about this part. So capture image frames, and then compress with Huffman compression, then store in SD card. So payload, okay, after you store in the SD card, now the OBC is responsible for reading the payload data. But as I said, each board has its board insert. Insert with HT. This is supposed to be unit 8. So it's as simple as this, that you get to know when, or rather if you have inserted this payload board into the CubeSat stack, a 0 or a 1. Something like float board temperature. So I have some NTC on the payload, on the camera itself, so you can like tell the temperature of the board, because cameras are CMOS and CCD devices, so they are very susceptible to heat, like board temperature. Yeah, I think that's that for now. I will deal with this later. These are a whole different subsystem. And yeah, so for now we can work with these two for the payload with subject to change. And then we put that into the payload data type T. Now the OBC is the final boss, right? So you realize that the OBC just reads data from all those other boards. So it reads the comms data, reads the EPS data, the payload data, right? And then it has its internal OBC data, right? So it has its own onboard temperature, it has the flash memory, it has things to do with RTC, it has to do with the EEPROM, it has things to do with the SD card values, it has things to do with what else can we read? Okay, those are the most primary one. Flash memory, RTC, SD card. So these are objects. I have not defined them yet, but I'm just explaining my design approach. So the OBC encapsulates all these other boards, right? So it's some sort of a nested, some sort of a very well nested structure, right? So for example, if I want to get the comms board temperature, and whatever is transmitted to the ground station is the OBC data, right? So what I'll do is just create an OBC data, let's say X. Then I can say X and go to, okay, this is a pointer, and say X dot whatever I need, let's say OBCX. Okay. Let's say we create a data point, OBC data T or D, for example, right? Then you can say something like od.comms data T dot something that is on the comms data point. Let's say comms data dot board temperature, if we want to get the board temperature for that comms board, right? Like that, comms temperature, right? So it's an error because it's not inside a calling function, but this is how we are going to refer to it. Basically, I'm going to be using a lot of like pointers to do that, but I'll I'll create a whole video showing the testing part of these data types and data structures. Yeah, so I think that's it for this video. I don't want it to be long, so these again is subject to change. A lot of these data points are subject to change because the development is active, but I just thought I should make a video showing the progress of the telemetry data points. And yeah, this should be good. So thank you for watching, and see you on the next video.